this seminar series.
Thank you so much for hosting me. So I will talk about a research program that has been going on for a while, and there have been several current and former graduate students now involved in it, as well as several National Science Foundation grants. So I want to know I can stand. As you may or may not know, psychology is currently in a state of crisis, so there's a big debate about the extent to which psychological findings can be replicated from one study to another. So I will talk specifically about decision making and connect that a little bit to the replication issue. So we'll talk about the construct behavior gapping, behavioral decision research, and how that connects to replicability. The replicability part is really only at the beginning of the talk. Later on I will, most of the talk is about bridging this gap and solving the problem that I stated at the beginning. So let me introduce you to a couple of reasoning fallacies that maybe you're familiar with. One of these is the fallacy of sweeping generalization. It's an invalid line of reasoning from the general to the specific. So a straightforward example would be the following. An elephant is heavy, therefore some of its molecules are heavy. Clearly this doesn't make any sense. Nonetheless, we have reasoning like this quite often in science and in psychology. The model or theory models aggregate behavior, therefore it models some or maybe even all individuals. This is a reasoning fallacy. It doesn't make any sense. Another reasoning fallacy that's quite interesting here is the fallacy of composition. This is an invalid line of reasoning from the specific to the general. So again, a straightforward example would be every molecule in an elephant is tiny, therefore the elephant is tiny. Doesn't make any sense, does it? And yet, this kind of line of reasoning is quite common in psychology. Every prediction derived from a theory models some individuals, hence the entire theory models some individuals. This is a very standard line of reasoning in psychological research, and unfortunately it has a reasoning fallacy right at its core. All right, let's focus in on a very specific paradigm in psychology and neighboring disciplines. Let's talk about decision making. And I'm just going to pick a theory, a prominent theory that you may know about. It's not important if you don't know. Cumulative prospect theory is probably the most prominent theory of decision making out there. And it's a theory that describes relatively simple decisions, such as, for example, if you need to choose, you have a chance of winning in some reward X with probability P and nothing otherwise. So the details of this theory are not important. I just want to point out a couple of things. So according to the theory, you take the reward you get and you transform it into a subjective perception of the reward. For example, using a function like this with some parameter alpha. And the probabilities are also not treated as probabilities, rather they are subjectively represented through some function, this called the weighting function, that describes how subjectively you receive the probabilities. And the whole theory, among other things, is designed to model that people overweigh small probabilities, treat them as if they were bigger than they actually are, and underweigh large probabilities, treat them as if they were smaller than they actually are. That's the reasoning behind these formulas. But what we really just need is that there are these formulas with parameters gamma and alpha. The rest is not really important right now. Now, this a decision maker who has a value of gamma over here that's between 0 and 1 overweighs small probabilities, which means that for small values of p, W of p is bigger than p. That's one of the features. Right. Here's an example of such a weighting function. So it overweights small probabilities and underweights large probabilities. You have the probabilities on the horizontal axis and weights on the vertical. And there's the one of those utility functions, like the one that I just showed. So these are extremely prominent. This theory won the Nobel Prize in economics. It's a very prominent theory. Well, in their original 1992 paper, Tversky and Kahneman, who proposed this theory, ran experiments, and they provided estimates of the parameters of the theory, including alpha and gamma, and actually additional parameters that I haven't mentioned. And you see that gamma is 0.61, so the median estimate is 0.61. So since the median is smaller than 1, it's correct to say that most people appear to overweigh small probabilities. It is more than half of the people, right? The median is smaller than 1. Now for gambles that involve losses, there's a similar parameter that's called delta, and that's also, its median is also smaller than 1. And so it's also logically correct to say that according to this finding, most people seem to overweigh small probabilities in losses. But it would already be a reasoning fallacy, and you will read this in many papers, unfortunately, even though it's incorrect, that this implies that most people overweigh small probabilities for gains and losses. That doesn't follow from the median. Now, quite a number of other papers will take these values and pretend that these are the actual parameter values of people studied in previous studies, but of course the fact that the medians are these values doesn't imply that even a single person satisfies cumulative prospect theory with exactly these values. So these are very common mistakes that you find in the literature using or citing cumulative prospect theory. Now, I want to explain very specific problems, so let's just, for the sake of example, take some lotteries. So here are the rewards and the probabilities with which you can win them. They don't really matter, I just want it to be complete. And now we can take this alpha and the gamma parameters, and we can vary them, and we can figure out what are the possible preferences that people could have, depending on what their alpha and their gamma values are. And so, for example, one preference pattern, so a zero really knows that you prefer the second option in the pair. So all of these zeros mean that you prefer B to A, C to A, D to A, and so forth. So this is one preference pattern I can construct for these lotteries. There's another preference pattern I can construct just by changing the alpha and gamma values. And in fact, a grid search of the alpha and gamma values with very fine step sizes gives me hopefully a more or less complete list of all the preferences that I could model with cumulative prospect theory with the constraint of overweighting. This is the standard story behind cumulative prospect theory. So requiring the weighting parameters to be smaller than 1. So, oops, I'm sorry. Out of 1,024 patterns that you could create, 12 are compatible with cumulative prospect theory. So it's a relatively restrictive theory that it only allows 12 out of 1,024 possibilities on these lotteries. All right, so now let's have a closer look at reasoning fallacies in behavioral decision research and how they relate to the replication debate. So we're going to assume that we somehow know the population, and suppose we have a population where everyone satisfies cumulative prospect theory with overweighting. So everybody has a preference among the 12 I showed you. Let's suppose that we even know the population distribution of preferences. We know exactly what proportion of the population has which preference. Let's pretend that there are no errors. So we have perfect knowledge, no errors, no response errors. This is as if we could 100% replicate whatever it is we're looking at, right? In a real study, you're going to have to worry about measurement error and not knowing the population distribution. So that's where we need replication studies. But here, we pretend we know everything. So it's like a best case scenario. So dropping these assumptions and adding statistical inference from data worsens the problems with the fallacies that I will talk about. So let's take these 12 preferences, and as I said, let's imagine we know the population. So imagine 1/3 of the population has preference state 4, 1/3 has preference state 5, and 1/3 has preference state 12. And now let's have a look at one of the very, very common measures that's used out there to evaluate the quality of a theory, of decision making. So a very common approach, which I call the heuristic of goodness of fit, because it's not logically accurate, but it seems plausible. The method theory is the one that makes more correct predictions. Doesn't that sound reasonable to you? That's why it's so heavily used. It sounds perfectly reasonable. So a correct prediction is used as a tally. The correct prediction tally is used as a measure of goodness of fit. Well, let's have a look. We know the population here. For every single prediction, we can compute how good this goodness of fit is. And so if we take the first preference pattern, in this population, that I just blanked out all the preference states that nobody has, 14 out of 30 preference pattern can account for 14/30th of all errors choices in this population. And I can fill this in for every preference pattern. And then I can see, well, there's, first of all, none of these numbers get very, very close to 30, so you could say, oh, cumulative prospect theory doesn't do a very good job in accounting for this population. Although I fabricated this population in such a way that everybody satisfies cumulative prospect theory. Good. Because you're hung up on something that makes no sense, which is you take one preference pattern and try to let it account for everybody.
So if everybody has preferences 4, 5, or 12, why are we looking at the fit of preference 4?
Well, I want to put myself in the position of a scientist who doesn't know the distribution, who uses this approach, and they would look at each of the preference patterns and see how well it does in accounting for the data. So in this population, assuming no error whatsoever, you would account for 14/30 of the data with preference pattern.
So I will ask this question because I'm confused too. Where did this 14 come from?
Because there are 14 zeros here, and that gave each of the 3 preference states equal weight. So, yeah.
So there's
So if I
7
have,
places where
there are 10 pairs.
it matches preference 4, and 7 places where it matches.
So, for example, it prefers that you prefer C to B. And 1/3 of the participants of the population prefer B to C, so here it makes the wrong prediction. 1/3 have this preference where it says you prefer B to C, and that's the correct prediction, and here's another wrong prediction. And if you aggregate all together, there are 14 correct out of 30. And since I assume that we know the population, that there are no errors, I would know best case scenario how well this preference pattern would explain the data if I had a good sample from this population. Now things get really crazy in a moment. Once you look at what is the largest number here, so the preference pattern that can account for the most is preference pattern 6. So this is, by this standard criteria, this is the best fitting preference pattern, but nobody has that preference pattern. Not everybody, but nobody has that preference pattern. But that is the best fitting preference pattern by this method. So maybe it's straightforward to you from the start that this is not a good method. Counting up things over a bunch of rows doesn't make any sense, and this is just a complete example. I think this is once more the same. Yeah, I just deleted all the other things. So this is the pattern that does the best, but nobody has that pattern. And so, there are two strange things here. First of all, nobody has the best pattern that explains the data best. And also, none of these numbers look very good, even though everybody actually satisfies this theory. So, counting up correct predictions just is not a good idea. Especially if you have a theory where some predictions are opposites of each other. Then it doesn't make sense to count things up. Well, anything could happen. All right, let's have a look at another very common method of evaluating a theory in decision making. And that's the heuristic goodness of fit method using modal choice. Again, it seems perfectly reasonable on the surface. A good theory predicts what most people prefer. Doesn't that sound reasonable here? It even seems pretty lenient. We would probably want to do something like that. But that actually does not make any sense, as I will show you in a moment. So modal choice is as an indicator of goodness of fit. Well, let's take the exact same distribution again. 1/3 of the population has preference 4, 1/3 has preference 5, 1/3 has preference 12. What's the modal preference? Well, in column 1 I have 3 1s, so the modal preference is 1. In this column, for example, I have 1, 0, 1, so the modal preference is 1. So you can go across and look at every column, and you will find that the modal preference, once again, exactly preference pattern 6, which once again nobody has. So, what most people want or prefer actually is no single person's preference. And those of you who are familiar with social choice theory should recognize this as just a variation on the Condorcet paradox. That's all. had earlier, the 1/3, 1/3, 1/3, let's call that the treatment population. And let's say the control population has preference pattern 6, 1/3 of them, and 2/3 have the opposite preference, which violates curative prospectivity. So now let's just zoom in to make things less complicated. Let's zoom into just these 3 pairs. And now we're going to compare the treatment with the control and see what that seems to tell us. Well, in the treatment condition, 2/3 prefer E to A because of the 2 zeros and a 1. So 2/3 of the treatment population prefer E to A, 2/3 prefer B to C, 2/3 prefer D to B, whereas in the control group, 1/3 prefers E to A, 1/3 prefers B to C, and 1/3 prefers D to B. So if I collected enough data, I would find this, and if I collected a huge amount of data, I would even conclude that I have a huge effect. Psychology usually works with so-called small effects. This would be a huge effect, and it would tell me that in treatment, it seems like the treatment leads people to prefer E to A, because this is so much bigger than that. Treatment leads people to prefer B to C, because this is so much bigger than that, and so forth. And with each additional prediction, I'm adding more evidence for my theory, my theoretical prediction. But this is completely wrong. Why is it wrong? Because actually in the treatment condition, nobody has this combination of preferences. This E to A, B to C, E to B, that's preference 6 again. So it's again the example where I've already recycled a couple of times. Nobody actually in the treatment condition has this preference. Whereas in the control condition, in fact, 1/3 have that preference. So just comparing treatment to control, one prediction at a time completely misleads me to draw the exact opposite conclusion from what is really going on in these populations. So this is the third fallacy, the fallacy of convergence to significant evidence. So let's take a little moment here to pause, because this is kind of like 2 talks. So I wanted to tell you 3 problems that we face in behavioral decision research and in psychology broader, and the rest of the talk will be about how to solve the problems. But if you have any questions up to here, maybe we should clear those up. Yeah?
How often do you get this sort of combination of factors in real samples of people's decisions?
Unfortunately, that is exactly the right question to ask. How much should I worry about this? This is a thought experiment. Unfortunately, this is the default. I did not have to work hard. It's like the easiest, when you try something and basically it's going to be like this. So if you think about studies that have multiple experiments and have effect sizes for each of them, if you ask yourself, okay, if there's a small effect size, that could mean that some small portion of the population behaves as the theory predicts. And if these are different samples of people, you could have a small proportion that behaves as theory, first prediction, a small proportion that behaves as the second prediction. Now you have to ask, well, how many behave as both predictions? And that will be even smaller than either of the 2. And the more predictions you add, the tougher it becomes to be able to say that even anyone satisfies all of the predictions jointly. But that's what the theory is, right? The theory is the conjunction of all of its predictions. So this is a fundamental problem with papers that make a bunch of different predictions and test each of them separately in separate experiments on different people. Yeah.
So there's an example of this when it says the medicine reduces cholesterol and fat and shoe size, but like really it's only reducing those things for like different people.
Right. That's a way to think of it. Yeah. And it doesn't do it for anyone jointly.
Right. No one gets all 3 of them.
Right. And unfortunately, things work against you. The more predictions you make, the harder it is to satisfy all of them together all at once in the same person. So that's where this problem becomes particularly prominent. Okay, any other questions? All right, so then let's talk about how we would solve these, and this is going to be, I will not be able to talk about everything, so I will skip stuff here or there and just see what seems more deep. So, wow, what's going on here? There's no button for that, right? typical decision-making experiment to test cumulative prospect theory, I would be offering you the choice between two games of chance. Imagine it's a wheel of chance. We spin it, and if the spinner stops in the shaded region, you walk out of the lab with $4 in your pocket, otherwise nothing. Or in this lottery, you have a slightly smaller probability of winning a little bit more. So that's a typical setup in an experiment like this, where you can either have a higher chance of winning less or a smaller chance of winning more. You have a trade-off between probability and reward, and these are once more the functions I had shown you. So I might have a whole bunch of such lotteries, and I might collect a bunch of data. How many times a person picked one choice over another. And let's see, how much of this do I want to say right now? Maybe just that the last two columns are actually real decision makers from my laboratory. Each decision maker made each paired comparison 20 times, spread out over time and separated by other choices. And this decision maker here is a hypothetical one. Just to kind of make the point that maybe if you didn't know how people behave, you would say, well, if this theory is doing a good job, I would probably, when the theory predicts you prefer gamble 1, I would see that maybe 90% of the time in a person. But in actuality, there's a lot more variation in actual choices than you might expect if you have around you with subject experiment. Yeah?
The game is exactly as you described it. Probability of winning and the reward.
Yeah.
And do they know probability, the people who take the test?
No, we deliberately only show them this field of chance. So they have to rely on a visual system to somehow
So they
evaluate
can
how likely.
quantify it, right?
Yeah, we don't give them numbers.
Okay, you don't give the numbers. Okay, so the whole thing...
There are experiments also that give numbers, but in my experiment, the data I just showed you, we use these. It varies from one experiment to another. This is the standard we use. Is that all you want to know for now? You're good? We'll see later. We'll see later. Okay. So I just took one of the predictions for cumulative prospect theory, and it predicts that you prefer gamble 1, gamble 1, gamble 0, gamble 0, and so forth for these pairwise choices. And then I could count how many choices they made as the theory predicted. Remember, that was the first heuristic. And for example, this decision maker here had 67% correct choices as the theory predicts. This person had 53%. But I could count on how many pairs the person picked what the theory predicts more often than something else. So, for example, here the theory predicts gamble 1, and the person picked gamble 1 17 out of 20 times. So that's more than half the time. Then I underlined where the modal choice disagrees with the theory. So of the 10 pairs, it's just one where the person picked something else more often than the predicted preference. Whereas this person has several places where they picked inconsistent with the theory more often than not. So this person has 8 or 9, depending on whether you count ties as modal choice, that are as the theory says, and this one has 4 or 6. But I will show you in a moment that this person actually is much better explained by cumulative prospect theory than this person, despite these seemingly opposite conclusions. So let's skip this for a second. So the thing that we need to accomplish is that the theory that I showed you, this cumulative prospect theory, it's just algebra. And the data that we obtain from participants are fundamentally uncertain. People fluctuate in their choices, they're uncertain about what they prefer. So basically we want to bridge the gap between deterministic theory and random sample data. That's what the title of my talk really was about. The hypothetical constructs versus the behavioral data. So how do you take something like a preference ranking, a utility function, and then hire theory, like cumulative prospect theory, or whatever it might be, how do you take that and relate it to probabilistic data? Well, there are basically two steps. Two natural steps. One is to take the algebraic theory and make it into a probability model somehow. And then the second model would be to figure out some kind of statistical methodology to evaluate the quality of the probabilistic model against a finite sample of data. So many of the things that I will talk about for the rest of the talk have a common feature, which is that you have some probabilities that are constrained in a particular way. So that's, also a lot of what I talk about will be geometric, just like this. So let's think about things in a geometric way. So I take the lottery pair AB, and I could record the probability of choosing A over B that's somewhere between 0 and 1. Let's suppose my theory requires it to be bigger than 0.5. So that probability needs to be in this range. And the probability of choosing A over C could be anywhere between 0 and 1, but let's say my theory requires it to be less than 0.5. So it has to be in this range. And imagine that the theory says the probability of choosing B over C has to be smaller than 1/2. So then jointly, the probabilities have to be in this shaded cube. I can also plot the proportions of choices in the same space. So that's there is an example to show of a person who picked A over B more than half the time, so it's on the back half, but they picked A over C more than half the time, so that's why the proportions are not inside of the shaded cube. And the statistics question that poses itself is, could these proportions have been generated by probabilities that belong to this cube, and just by sampling variability, because we have a finite sample, we ended up there rather than in the cube. And this is called order-constrained statistical inference. It has been a very, very tough problem in mathematical statistics for many decades, but this inference problem has been solved in the last half decade or so. So we're now able to do really nice statistical analyses that use this kind of thing. So there's a Bayesian set of solutions for problems like this that has been proposed about 11 years ago. And my former student in his first semester in grad school solved the frequentist analog. So he figured out how to test the hypothesis that data that are lying somewhere in a space are generated by probabilities that are order constrained. What's the problem here? I guess I forgot to tell you what the problem is. If I find the best, the so-called maximum likelihood estimate, that will be a vector of probabilities that will lie on the back face of this cube. And that's the boundary of the parameter space. And at the boundary of the parameter space, the so-called likelihood function goes crazy. And people have not known for many years what's the distribution of that likelihood function. It turns out that if you know the geometric shape of the space around that point estimate, is just a cube, but it could be some crazy shape. If you know the geometry of that shape, you can figure out the distribution of that likelihood function. That's what my student did in his dissertation. So basically, the statistics problem is solved, and I'm going to just now talk about the first problem, which is take a deterministic theory, how do you make it probabilistic. So we can start out with a deterministic preference. Imagine you have a person who prefers A to B to C and never makes a mistake. So the probability of choosing A over B must be 1. The probability of choosing B over C must be 1, and the probability of choosing A over C must be 1. So this corner out there of the unit cube corresponds to the deterministic choice, always A over B, always B over C, and always A over C. Now if we want to replace that deterministic model by a probabilistic one, basically you want to move from the corner into the interior of the cube to get probabilities different from 0 or 1. And there are all kinds of probability models out there in economics and psychology, and they basically vary or differ in how they go into the interior of the cube. So that's what I want to talk about a little bit more. The simplest approach to introduce probabilities would be to say, well, hey, even though I prefer A to B, I occasionally make a mistake. So in fact, this is one of the preferences in cumulative prospect theory with particular parameter values to link it back to what I talked about earlier. And so if I prefer I to J, I might not necessarily always pick it because I occasionally make a mistake. So if the error probability is epsilon, I only choose I over J with probability 1 minus epsilon. If epsilon is tiny, the choice probabilities will be right next to the corner. As the choice probabilities get bigger and bigger, I move along this line, and at some point, if I make errors more often than not, I end up in the opposite side of the cube, which would be, of course, ridiculous. So in most cases, it makes sense to require the error probability to be smaller or at most 1/2. In which case, we only have a line segment going to the center of the cube. Now, why should the error probabilities be constant? Why should they not depend on the things you are comparing to each other, that you're choosing among? So how about this? I prefer I over J if I likely than what you don't prefer. That seems like a fairly innocuous requirement. And it's shared by many models out there in the literature. So that, in fact, looks exactly like the model I told you when I talked about the statistics problem. And the data sets I showed you are shown here with the 3 dots. My hypothetical data set is right next to the deterministic theory, so it's almost perfect, but almost a perfect match. And here are the 2 decision makers that I had shown you. One of these those 2 decision makers has every single choice proportion on the wrong side of 1/2. So when the probability should be bigger than 1/2, he or she picked it less than half of the time, but only a little bit. And so it turns out that that person's data are close enough to the cube that it could have been generated by probabilities that are actually just barely in the cube. Whereas this other data set, which has 2 of 3 coordinates in this particular case, where the choice proportion is on the correct side of 1/2, and only 1 is on the wrong side of 1/2, that 1 is so far off that it just could not have easily happened by sampling variability alone. And so that's how we get these values here. So the hypothetical decision maker, well, those data were right in the cube. So the p-value of a null hypothesis test is 1. You cannot possibly reject the hypothesis. The person who had 3 choice proportions on the wrong side of 1/2 actually is not incompatible with the null hypothesis of satisfying the cube. And the one who had just 1 on the wrong side is 15. Well, 15 is really far away from 10 out of 20. And that by itself was enough to reject the hypothesis that this person was choosing according to this preference pattern, but made errors up to half the time for each pick. Now, you probably thought, wow, that would be really rather lenient. I'm allowed to make mistakes up to half the time? That's pretty lenient. How about we require something a little stronger? And well, we could, for example, require that if I prefer to J, I should pick alpha J at least, let's say, 3/4 with probability 3/4 or so. And all that does is that it restricts the binomial parameters to a smaller cube or hypercube, or actually in 10-dimensional space. I can only show you 3-dimensional projections. So, sorry. The hypothetical decision maker is still smack inside, but we don't actually have real decision makers that are so close to deterministic. And the other 2 are way out there and could not have generated with any statistical plausibility data over there with probabilities in it. Well, there are other models. If you know a little bit about the economics literature, or econometrics in particular, you may have run into these. Actually, I think these show up in all kinds of disciplines. So there are a whole bunch of ways to take deterministic theories and turn them into probabilities. The logit, the logistic, and the probabilistic Thurstonian are the most famous. Basically, since cumulative prospect theory gives each gamble a value, we can take that value, transform it somehow, compare the value between 2 gambles, transform them somehow, and get a probability from them. And that's what these formulas do. And these kinds of models work if you can define something like how much you prefer one thing to another. Each of these are ways to define how much you prefer one gamble to another. They don't work for theories that don't have numerical functions, so they are limited in that way. So I'm going to take 3 specific lotteries. It doesn't really matter, just it happens to be these 3, and I plug the lotteries into cumulative prospect theory and plotted the loose, logit, and probit models in the same space of binomial probabilities, and you get a sense of how they live inside of that cube. Remember, I had said that the key thing about all these models is they start from the corners where the deterministic preferences are, and then they somehow go into the interior to introduce probabilities from them. Well, what you may or may not have noticed is that if gamble 1 has a higher value than gamble 2, this probability, because they are the way these this is a normal distribution, and a normal distribution. Because of the way that these are constructed, you will automatically prefer the better gamble to the less like gamble with probability greater or equal 1/2. So that just means that the logit, probit models, and the loose choice model are all special cases of what I call of preference states. So here we have some number of preference states. They form points at the corners. For each point, I make a cube of length 1/2, of side 1/2. And the econometric models are nested inside of that disjoint union of those half-unit cubes. So in other words, if you were interested in maybe doing some econometric analysis of some data, you could use the cubes first with other constraint methods to kind of screen your data to see whether one of these econometric models has a chance of accounting for the data. If the cubes then account for the data, no need to explore all the different variations of econometric models that are nested inside of it. So that's one of the things we can do. All right, let me skip a couple of things here. Let me skip these so that we get to, because we don't have that much time left, let's get to these ones. So there are other models, but I want to emphasize these. I think these are the most interesting from definitely from a psychology point of view. So in the previous class of models, the idea is that the person has a fixed preference or even a fixed utility function. We don't know what it is. We create probabilities, and then we consider all possible scenarios. That's how we glue cubes together or make entire clouds of probabilities. But what if, rather than having a fixed preference and making mistakes with some probability, what if the preferences themselves are probabilistic? I'm sure you have had plenty of occasions in your own life where introspectively you are just genuinely uncertain about what you prefer between two options, especially if you face trade-offs between attributes that are just hard to compare with each other. So here the idea is that the preferences themselves are probabilistic, and it's not a matter of not making a mistake when you respond. So in a random preference model, you have some set of preferences. They all have probabilities, and the probability that you choose x over y, that's missing on the left here, is just the total probability of all preference states in which x is better than y. Or you could have the utilities of options could be random variables that have some joint distribution. The probability that you pick x over y is the probability that x has a higher utility than y. So the utility functions are replaced by random variables. Or we could put some probability measure on some appropriate space of utility functions and take the probability of all of those functions which assign x a higher value than y. These three kinds of models are closely related to each other. In fact, the binary choice probabilities are consistent with one of these three, if and only if they're consistent with the other two as well. So this kind of model looks very, very different geometrically. And this is, I suspect that for many of you, this is more interesting math that comes into play. So if you take, for example, that so I'm moving away from cumulative prospect theory and just allow people to rank all the options from best to worst. If I have only 3 options, I have 1, 2, 3, 4, 5, 6 possible rankings. And again, if a person had one of those rankings and deterministically always chose according to that ranking, the binary choice probabilities would be at one of the corners. Now, imagine that you have half the time you prefer A to B to C, but half the time you prefer B to A to C. What are your choice probabilities? Well, you choose A over B with probability 1/2, and the other two choice probabilities remain 1. So in fact, that's this point here. If I take any probability distribution over all 6 preference states, what is that? Well, that's actually a convex combination of the 6 vertices that correspond to these rankings. And so any point in this convex polytope corresponds to a probability distribution over the 6 preference states. So this is, again, a model constraining choice probabilities. It's another constrained model. We can use these fancy newer statistical methods to test this kind of model on laboratory data. This model also includes the loose choice, logit, and probit models as special cases again. So that's kind of interesting. Earlier we saw them nested inside of these cubes. They're also nested inside of this linear ordering polytope. That's because they're so-called random utility models. This model here, the big polytope, allows for any joint distribution of the random utilities, whereas logit and probit models are parametric families of distributions, so they only occupy certain parts of that larger space. So the big polytope, in a way, is could be, once again, used as a screening tool to see whether data have a chance of being consistent with an econometric model testing itself. Well, if we wanted to do this kind of build a model like this for cumulative prospect theory, instead of taking all the possible rankings of options, I would just take those rankings that are consistent with cumulative prospect theory. I consider all probability distributions over those rankings. They form the convex hull of these vertices, so they form a convex polytope. If I can figure out the geometric structure of that convex polytope, those of you who are familiar with convex geometry know that you can describe a polytope either with its vertices, or you can describe it with its facets, the flat surfaces of maximal dimension. Or there are other tricks, but if I know all the surfaces, so in this case these triangles that form the polytope, I can use the Euler constraint statistics results from the recent literature to test whether binary choice probabilities could have been generated by probabilities living in this space. And I'm going to skip this. I'm also going to skip this because I think we're getting very close. All right. Well, then I will, well, I guess I go back here for a second. How many of you know what transitivity is? I just wonder whether I have to explain what it is or not. So transitivity of preference means that if you prefer A to B and you prefer B to C, you must also prefer A to C. Of course, if your preferences are based on a utility function, if A has a higher utility than B, B has a higher utility than C, of course, automatically A has a higher utility than C. Now, there is a very substantial literature in psychology, economics, in biology, a whole bunch of different disciplines that have reported violations of transitivity in humans, in various kinds of animals. And that literature has unfortunately made a bunch of errors. So either they didn't solve the math problems I talked about, or they didn't solve the stats problems I talked about, or they didn't even use any math or statistics to begin with. They just did something not very clear that wasn't very precise to begin with. So in a very, very large project, we decided to test the linear ordering model. This is basically all transitive preferences and also complete and asymmetric. So we assume complete preferences and asymmetric preferences. So testing whether preferences are transitive or not amounts to testing whether the data are compatible with the linear ordering polynomial. So we're the first to run a test like that. We used some historic data from